In this week's homework, you're going to experiment with amortized analysis using the double-ended queue problem as an example. I'm going to give you an alternative implementation of a double-ended queue. It works, but the performance isn't great. Your job is to simply change one method to improve the performance. When it starts off, you're going to get a typical sort of quadratic style performance. Let me just show you when you run this thing. It works just fine, but I'm going to do a doubling test here, starting with 4,000 elements, then 8,000 elements, and I'm going to get some pretty dreadful numbers. In this case, I'm doing a video export in the background on my laptop, so the numbers are particularly bad, but I've got about 4 times the work for double the input, so characteristic of a quadratic algorithm. This is what I got when I ran it without the video export going on in the background. So your goal is to transform this algorithm from one which is quadratic time for in operations to one that's linear time for in operations. Of course, the output that you're going to get will have noise in it from systems effects and things like that, but you should see this basic improvement in the performance, and you should see this general convergence toward doubling the time for doubling the size of the input. So let's look at the problem. The problem here is to implement a double-ended queue, and if you think about it, it's quite straightforward to do this using 2 stacks. What I'm going to do is put 1 stack on my left, that's my left stack, 1 stack on my right, that's my right stack. And I can then push from the left onto the left stack, push from the right onto the right stack. That's pretty great. Is empty? Well, are they both empty? What's the size? It's just the sum of the sizes of the 2 stacks. This is obviously correct as long as I pop all the things from the left-hand side that I pushed on the left-hand side, and similarly on the right. It gets trickier to know what's going on in the case that I mix pushes on one side with the other side. The idea of this algorithm is to think of the 2 stacks as being opposed to each other. So what I'll do is let's suppose I push on my left stack. I'll push 1 and then 2 and then 3. Now, if I want to pop from the right, of course, the number that I should get on the right is 1. Well, unfortunately, that's at the bottom of my left stack. How can I get it out? Well, a simple idea is to simply push everything from the left stack over to the right stack. At that point, my left stack is empty, and I can simply take the top element of the right stack. Hey, that's great. How much work did I do? Well, it took time proportional to the number of elements that happen to be here right now. So this is the idea of the implementation of the double-ended queue using stacks. The key method for accomplishing this is called move. And what move does is it takes all of the elements from one stack and puts them on the other. So we have a from stack and a to stack, and we're simply going to take all of the elements on the from stack, pop them off, and push them onto the to stack. We can use the move method then to implement pop. Pop left will check to see if the left stack is empty. If it is, we just move everything from right to left and then pop. Symmetrically, when we pop right, we just look to see if the right stack is empty. If it is, we move everything from the left and then pop. To understand the worst case complexity of this approach, we need to understand the worst thing that could happen. If I start off with all of my elements on one side and then try to access them from the other, well, I'll have to move everything to the other side. And in general, the worst thing that can happen is to alternate from one side to the other. So moving everything from left to right, then right to left, etc. Let's just look at an example of that. So if I have 1, 2, 3 on the left and then I want to pop from the right, well, I need to move all of those things over. So I'll end up with 3, 2, 1, and then an empty stack. At this point, I can pop the element, but let's suppose then I try to get from the left-hand side, which is now empty. Well, I have to move everything over. So I'll put the 2 and then the 3. Then I can actually pop from the left. At this point, my right-hand side is empty. So if I want to get from the right, I have to move everything over, and then I can pop it from the right. And you can see going back and forth, what's happening is that at each iteration, the size of the remaining elements is decreasing by 1. And if we start with in elements, we'll start off with in, then in minus 1, then in minus 2, etc., down to 0 or 1. And you can see that that sum is a familiar sum. It's the triangular sum, which is giving us a quadratic total. The test that I've written is testing precisely this load on the data structure. Let's just look at the main method real quick and the tests in it. So the main method here has a correctness test, which should be sufficient to ensure that you do not disrupt the functionality of the data structure by improving the performance of the move method. And then it has a performance test. The performance test is going to do this time trial repeatedly here. The time trial is pushing 2 to the n elements onto the left and then popping them by alternating right, left, right, left, right, left. So this is precisely the worst case load for this algorithm that I've given you. So how are you going to make it work better? How are you going to get this to work in linear time? Well, the key to realizing this is to note that we're moving too much stuff. We're just doing too much moving. So in particular, the problem here is that I'm moving everything from one stack to the other. Wouldn't it be nice if instead of moving everything, I just moved like half the things? So that would mean that instead of moving 3, 2, and 1 over here, let's say I just would move 1 over here. And that means that 2 and 3 would have stayed behind. If you can achieve something like this, it would be a lot better. But note that that's difficult to do directly with a stack, because in a stack, I can't just take the bottom element off. What have I got to do? Well, I've got to somehow take off these top elements first. Then I can move the bottom element, and then perhaps put these things back where they were. So overall, that sounds like I'm doing more work, not less. But this is the funny thing about amortized analysis. By doing more work in one method, I may improve the performance overall. So this is the area you need to explore. Unlike previous homework assignments, there's not a huge amount of code to write here. This is mostly a thought experiment. You'll find that you don't need to do very much. The answer here will be 3 or 4 lines of code at max. I've written out what you need to do. You need to make it perform better. And I've given you a little bit of a hint here, which is that you can use a temporary stack to help you do this. I've also said maybe you need to do some debugging while you're getting things to work. You could uncomment these print messages. You might add more print messages in here. If you're going to be printing and debugging, you'll probably want to comment out the performance test so that you can just zero in on correctness to begin with, and then try to get the performance back. Good luck with the homework.